Good evening, everybody, and welcome to this actual TWed. We're this semester, unfortunately, has been kind of thin on TWed talks, but we have had our fill of various technical tutorials and R Pirates meetings and that sort of thing in this time slot. We have a few more TWeds by idea or TWeds or idea talks by idea grad students or Tethos World grad students coming this term, as well as an end of the term TWed lightning talks at the last day of the term or closest to it on a Wednesday. So without further ado, I'll introduce Sabbir Rashid, was actually the first person to sign up to do a talk this term. Thank you very much, Sabbir. We really appreciate you stepping forward like that. Sabbir has done a number of TWeds over the past couple of years, and we're really looking forward to this one. So without further ado, I'll shut up and Sabbir, take it away. Thank you.
Thanks, John. Okay, so let me share my screen. Window. And okay, so you guys should see the full screen mode. Do you guys see it?
Yes, we do. Thank you.
Okay, great. Thank you. Okay, so this talk will be somewhat informal in a sense, where pretty much we are submitting a resource to the International Semantic Web Conference where we created a reasoning framework within WIS, and we're calling it SQuARE, the SPARQL Query Agent-Based Reasoning Engine. So in this talk, I'll go through some kind of like introduction and motivation of this and go through some of the implementation details, as well as some of the resources that arose from this project. And I won't spend too much time on stuff like related work, just so we have enough time at the end for discussion. So I'll begin by introducing SQuARE and some of the motivation for this work. I'll briefly discuss some prior art, including description logics, reasoning engines, and validation approaches. And then I'll go into our approach for creating a custom reasoning engine. And when we were testing the functionality of this engine, we pretty much created example RDF snippets for each OWL axiom that we implemented. And then the collection of those examples we use to create a validation ontology so that others can validate their reasoning engines in a similar way. Then I'll briefly go through our complexity analysis of SQuARE. And finally, I'll conclude with some closing remarks and some references to resources that we have created. So I'll begin by introducing SQuARE and some of the motivations for this work. So SQuARE is the SPARQL Query Agent-Based Reasoning Engine. So the way we went about creating this engine was that by examining the kind of representation structure of the OWL-DL axioms, we were able to represent each axiom as SPARQL construct queries. In the implementation section of this talk, I'll talk about this in greater detail. We implemented this reasoning engine within an existing knowledge management framework, WIS, which includes an agent-based architecture, which was part of the reason why it made sense to implement it within this framework. So pretty much WIS, you can program agents that trigger when there are graph updates. So if new knowledge is added to the graph, an agent can be triggered. And this becomes useful for our approach, which I'll discuss later on in this talk. And then the combination of all this together pretty much resulted in a reasoning engine. And this is a little bit different from existing engines because existing reasoners like Pellet or Hermit, the user can, to some extent, specify which OWL profile is being used or which axioms are being run. But for the most part, there's an existing profile that gets run. And it's also difficult for users to customize the reasoning engine to create their own rules or their own reasoning profiles. So our approach allows us to do that. So pretty much this work arose as a step towards hybrid reasoning. So for my thesis work, I'm working on a way to get towards abductive reasoning, which is a non-monotonic form of reasoning that can be used to hypothesize why certain assertions exist in a graph, for example, or to like come up with diagnoses for a medical condition. And other forms of reasoning may be like abstraction or induction. But in order to do this hybrid reasoning, we needed a framework for including each form of reasoning in such a way that one form of reasoning may result in another form executing. And this kind of goes back to this agent architecture I mentioned before, where pretty much an update to the graph may result in another agent executing. So you can imagine a deductive inference resulting in new knowledge added to the graph. And then once that knowledge is seen, maybe another deductive agent runs or a different kind of reasoning agent runs. So this work is a step towards the creation of a hybrid reasoning system that can do multiple forms of reasoning in conjunction. This approach also allows for the coexistence of conflicting information. So if anyone's run a reasoner through maybe Protege or in a standalone way, as soon as that reasoner comes across an inconsistency, an error message is given, or it gives an explanation for why the ontology is inconsistent, and then the reasoner stops executing. So pretty much if you have an inconsistent knowledge graph, then you can't really reason over it. However, because we're doing graph queries and updates, and triple stores allow for inconsistent information to exist in the triple store, our approach actually allows for reasoning over a graph that has inconsistent information. So this might be useful in like a fake news application or in a disease diagnosis type setting, or wherever, maybe like a journal type, fact checking type of thing. So there may be applications where you need this inconsistencies, and traditional reasoners don't allow for you to reason over those, but our approach does. And finally, as I mentioned before, our approach allows the user to create their own reasoning profiles or their own custom reasoning rules. And this work actually, early version of this work was applied in the breast cancer setting where we created custom reasoning rules to infer the stage of breast cancer patients based on the previous stage, or based on stuff like their tumor size, the number of lymph nodes affected, whether or not the cancer spread, and certain hormones, stuff like that. So this approach has been used in the past, and this work is kind of like the formalization of that approach. There's three main contributions of this work. So as I'll mention in the next section briefly, there are SPARQL construct-based reasoning approaches or SPARQL ask-based. However, these existing approaches don't publicly make available the queries. So So probably the most popular of these approaches is SPIN, which is the SPARQL inference notation um, framework, which kind of defines its own vocabulary to do queries to represent um, SPARQL queries. And there's been work done in representing OWL-RL in terms of the SPIN architecture. However, I think this work is proprietary of Top Quadrant, and without a paid license, you can actually view the complete set of queries. However, we make our queries publicly available. So I'm going to click this link and hopefully it's still visible. So if it's not visible, let me know. But you should be seeing our resources webpage. And then you have different types of axioms, so class inclusion. Um, and I should also include the OWL-DL version of the axiom, but pretty much class inclusion relates to a class being a subclass of a superclass, then it's the subclass of all the superclasses. And this is how it's represented as a SPARQL query. We also include examples of RDF that would result in um, this axiom being executed. And I won't go through all of them, but pretty much there's a bunch. So let's go into the table of contents. So we have stuff like class inclusion, individual inclusion, property inclusion, equivalence, disjointness, transitivity, reflexivity, symmetry, functionality, inversion, domain and range, data type restrictions, assertions, keys, existential quantification, universal quantification, self-restriction, enumeration, cardinality, disjunction, intersection, negation. Um, yeah, so this resource is made publicly available, so anyone can just use our construct query for a particular OWL rule. So now back to the presentation. So pretty much we've also incorporated this reasoning framework into WHYIS, which is an open source knowledge management framework. So this is a contribution because it demonstrates that we're not just talking theory here. We can actually implement these SPARQL construct queries to actually do reasoning within a knowledge graph or an existing knowledge management system. And again, this tool is open source, so our implementation is also made publicly available. So if someone else wants to do their own implementation or they want to use WHYIS to run this reasoning framework, they're able to do so. And our third contribution is the ontology that kind of arose from this work. So in order to validate each of the OWL-DL axioms, we created RDF examples, which would result in the execution of those axioms. And some of these axioms result in inconsistencies, right? So you have the resulting inference is that the resource is inconsistent. So, however, something like Protege might not be able to run over an inconsistent ontology. So we include both an inconsistent version of the validation ontology as well as a consistent version. And I'll be talking about this a little further, but pretty much back to these axiom examples. The examples you see are pretty much, so we adopt existing SIO classes where applicable. If there is an example of that within SIO, or we create our own instances or classes if that's also applicable. So these collection of examples that you are seeing here are what make up the validation ontology. I was trying to go through one where we created our own class. So we're just seeing mostly our own instances over here. So for example, this example of a key, we created the value unique ID class, where valid person has a unique ID. So over here, John and Jack have the same unique ID, so then they must be the same person, right? Okay, so back to the slide. Okay, so I'll briefly mention some related areas, but I won't go into too much detail, just for the sake of time. So pretty much we are encoding each OWL-DL axiom as a SPARQL construct query. So the full set of OWL-D axioms, however, are not tractable in the sense that if you have all of OWL-DL and you run it over a knowledge graph, there's a chance that your the inference engine won't complete running, right? And so in order to address this, several OWL2 profiles have been created, which kind of trade tractability for expressivity. So the most famous OWL-DL profiles are like OWL-RL, which is the most expressive one, or OWL-QL or OWL-EL, which is the most efficient one, right? So pretty much you have these OWL profiles. There's also stuff like OWL Lite or OWL2 Lite, which are pretty much subsets of OWL-DL. So our approach, we've encoded each OWL-DL axiom, but we can also specify the profile you want to use. So you probably don't want to use all of OWL-DL, but you can specify you want to use OWL-EL, which contains a subset of the axioms, or you want to create your own reasoning, your own OWL profile, essentially, which maybe includes only the inheritance axioms or something. Or you created your own custom axioms, which your profile specifies. So also some related work relates to existing reasoning engines. So probably the most popular of these are Hermit, Pellet, Racer, and Fact++. And most of these are written over Prolog. I won't go into too much detail here, but they also implement a certain OWL profile, a tractable profile. For example, Pellet implements OWL-RL, I believe. And then finally, there's some related approaches related to validating existing graphs using like shackle, the shape constraint language, or in terms of representing rules as SPARQL queries, such as the SPARQL inference notation. Pretty much I refer the viewer to our paper that we'll be submitting to the International Semantic Web Conference research track for a further discussion of how this work expands on the prior art. So next I'll be going into a pretty quick discussion of our implementation. So we describe our approach for creating a custom reasoning engine. So pretty much in a broad, in a bird's eye view, we formulated each OWL-DL axiom as a SPARQL construct query. And I'll go through those again for the people who join late. But pretty much we make each of these SPARQL construct queries publicly available online. Then the next step was we wrote inference agents in YIS to query and update the graph. So we've implemented both forward chaining and backward chaining. So I mentioned earlier that one of the motivations of this approach is to move towards hybrid reasoning, where we're doing multiple forms of reasoning in conjunction, such as deductive with abductive reasoning. So to do backward chaining, which is given assertion in the graph, what are some possible ways that it got there, right? So I guess I can go through an example real quick. So if we go to this web page real quick. So pretty much class inclusion says that if you have a superclass which has a superclass, then the class is also a superclass of that class. So here you have material entity is a super, it has the superclass object, and object's a subclass of entity. So the reasoner should infer material entity is a subclass of entity, right? So in the graph, if we see material entity RDFS subclass of entity, then the backward chaining capability asserts in the nanopublication that this triple could have arisen from this class inclusion rule, right? So that capability is incorporated into WIAS. And then forward chaining is traditional horn clause inference where you have a consequent, an antecedent and a consequent. So if P, then Q. So we incorporate that form of deductive reasoning as well. Yeah, so we were over here. Pretty much we wrote these inference engines to look for these consequent patterns, antecedent patterns in the graph, and then to add the consequent back to the graph. And in order to make sure this was working properly, we had to write unit tests to check that the expected triple is being added to the graph. And in writing these unit tests, that's where we wrote these examples of each RDF form that we're expecting, which should result in the expected triple to be added. So it was through the writing of these unit tests that the validation ontology arose. So pretty much on the left, you have like a diagram of how this kind of works, where pretty much you can have, you can specify active OWL2 profile, such as EL, QL, RL, or your own custom profile, which then includes each set of axioms included in that profile. And the axioms are in the form of antecedent consequent. And based on that, we create a SPARQL query where we construct the consequent where the antecedent pattern is found, as long as the consequent doesn't already exist in the graph. So this filter not exist statement is pretty important because otherwise we'd be continuously adding the same information back to the graph. So this prevents that from happening. So an example of a SPARQL construct query is shown here, where pretty much if you have a key property with a key value, so a key property is pretty much defined by OWL has key and then the list of key properties. Pretty much it means that two resources that have the same value for the same key property must be the same resource. So we can construct that those two resources are the same. So an example is pretty much you have this key property unique ID where a person has that unique ID key. So John and Jack have the same value for the unique ID. So we can infer that John and Jack are the same, right? However, we also have the assertion John is different from Jack. So this example should result in an inconsistency because we're getting, yeah.
I was just wondering if I could ask a kind of a quick contextual question.
Sure.
So I totally get that these construct queries are modifying the graph, writing these in, but that raises all sorts of flags for me in terms of where are they getting written? Are they getting written into I'm thinking from a management standpoint. Are they getting written into named graphs? Are you relying on something else going on? Something specific that like perhaps WIAS is doing. I'm imagining applying these to in some way or writing these in some way to kind of a standard triple store, and if that's even applicable, what sort of accommodations are you making for writing these in?
Right. That's a great question, and I should definitely mention that in a future iteration of this presentation. It is included in the paper, but so pretty much what we're doing is we're creating a nano publication with the assertion. So we are creating a named graph, and the new information, the consequent, is being written into the assertion portion of a nano publication. And what's actually cool about doing this, first of all, Wise has built-in support for this. But secondly, when we create this assertion into this named graph form, we're also able to add an assertion into the provenance portion of the named graph, where we can say that we can provide an explanation for why this assertion was added into the graph. And that's done through templating. Yeah, that's a great question. I do discuss it in the paper. And so part of the reason that we're giving this presentation is because if the paper is to be accepted into ISWIC, then I'll have to present on it in the future, right? So getting some early feedback, like what you just mentioned, will make this presentation better when I have to present it in November if the paper gets in. So yeah, that's a good point. And I can even update the diagram to make that more explicit. But yeah, so we're publishing it in the form of named graphs, which are nanopublications, where the asserted information goes in the assertion graph, and the explanation for why it was asserted goes into the provenance graph. And I also mentioned we have back chaining capabilities. So the back chaining is also done using nanopublications, where I believe the publication info is populated to say that this assertion could have been generated from this given axiom. Okay.
So can
Yeah.
I ask? So have you
Yeah, go ahead.
finished? Have you finished your? Oh, okay. So I have a quick question. I have
go ahead.
a quick question. So I think you are using SPARQL to do some construct here. So but I know that there are some internal, reasoner there. So what's the purpose of you using SPARQL instead for this construction?
Wait, there's some internal reasoners where?
So for RDF reasoning, there are already some reasoners, right?
Mm-hmm. Right. So pretty much, why are we creating our own reasoning engine when stuff like Hermit or Pellet exists already?
Yeah.
Right.
So what's the difference between this approach and
right?
Yeah.
Yeah. So I'll just quickly go through this again. So so pretty much we're working towards a hybrid reasoning system, and in some sense, by creating our own reasoning engine, it allows us to more easily create the components for a hybrid reasoning engine. Also, we're able to use the SPARQL construct approach to do some form of abductive reasoning. So it made sense to go with a SPARQL construct approach. Also, so if you have a knowledge graph, and you upload it into Protege, for example, and then you try to use an existing reasoner like Pellet on that knowledge graph. If the knowledge graph has any inconsistencies in it, the Protege will output an error message saying that, like, oh, we couldn't continue reasoning because we found an inconsistency. Or sometimes the knowledge graph itself doesn't even get loaded completely into Protege because of the inconsistency. However, if you have inconsistent knowledge that is valid RDF, you can load it into BlazeGraph or Fuseki or a triple store, right? So a triple store doesn't prevent you from loading inconsistent knowledge, but traditional reasoners can't reason over inconsistent knowledge. So because we're doing SPARQL queries over a triple store in order to add stuff back to the graph, or to query for patterns within the graph, this approach actually allows us to reason over this inconsistent knowledge, which earlier approaches don't allow. And then finally, our approach allows the user to create their own reasoning rules and their own reasoning profiles, which, unless you actually update the code, existing approaches don't allow you to do that. Well, actually, so there are stuff like SQuARE and other language approaches where you can write your own rules, but and I guess some inference engines do support SQuARE, but for example, you can't necessarily change between OWL RL and OWL EL or create your own custom profile.
Okay, thank you for your answer. So maybe I can listen to the whole presentation and
Yeah,
then
yeah.
I can ask some other question.
Sure,
Thank you.
yeah.
Yeah.
No problem. Good question. Okay, so just a quick quote. Ever since I was a child, I have been a strong believer in the principle that to understand how anything works, you need to take it apart and look at it in detail. This principle that worked with toys also works pretty well with search. So I just included this quote because pretty much by building our own reasoning engine, I've had to go through each OWL DL axiom. I had to come up with examples that would result in the axiom executing. I had to test these. I had to run existing reasoners on each of the tests, as well as our reasoner. I had to do a complexity analysis. So pretty much by breaking apart the OWL DL, essentially, it helped me better understand in greater detail how each of these axioms work. So what's another motivation for creating, maybe not a motivation, but a benefit for creating your own reasoning engine? Well, it's a good way to really learn OWL in its intricacies. Okay, so next I'll be talking a little bit about the validation ontology. So as I mentioned already, the validation ontology arose from our testing of this reasoning engine that we've created, and it includes examples of each OWL-DL axiom. So pretty much we've created this website for the validation ontology, which pretty much includes the SPARQL versions of each axiom, as well as examples from the ontology that will result in the axiom executing. So for example, we can represent class disjointness as construct resource is type nothing if the resource is a type of class and it's also type disjoint class, where either the class or the disjoint class are disjoint with each other, right? So pretty much in the ontology, then we include we pretty much root the ontology in SIO. So we find examples within SIO where we can, or we create our own examples. So pretty much SIO has this concept of real and virtual and fictional, where they're disjoint with each other, right? Real is disjoint with fictional. So then we create an instance of an imaginary friend that is both real and fictional. So the reasoner should infer that the imaginary friend is of type nothing, which is pretty much the triple form of saying that the graph is inconsistent. So if anything is of type nothing, then that means there's an inconsistency. All right, so we have this for each of the OWL axioms. We have the SPARQL construct query representation. We have an explanation. So I mentioned before as well, from answering John's question, that we construct the assertion into a nanopublication, and we include an explanation into the provenance graph of the nanopublication. So pretty much this explanation is a template string where stuff like restriction, list, well, I guess we just have restriction and list here. And oh, I guess member should also be italicized. They correspond to variables within the query, and they get resolved into the actual resource that is being executed over. So, for example, if this resource had a name like disjoint restriction, we see that since disjoint restriction is all disjoint restriction with classes listed in this list over here, then each member of the list are disjoint with each other. Something like that. So we used templating to resolve the variables to the actual resource. Right, so there's also Widoko generated documentation for this ontology. So we have a consistent version of the ontology available as well as an inconsistent version. And then we have the documentation here where you can see which classes are being used, which properties are being used, which data type properties, and which individuals are there. Yeah, so this was just generated using Widoko. Yeah, you guys can play around with this yourself. And then it has some of the things like, for example, alive is equivalent to not dead and stuff like that. So we have documentation for this ontology available and linked from this web page, which I'll include the resources link, which is included at the end of the presentation. Okay, so I'll quickly go discuss our evaluation slightly, but I won't go into too much detail since the reader will, or the viewer will eventually be referenced to the paper which we're submitting. But pretty much in order to evaluate the complexity analysis of SQuARE, we created an axiom mapping to each OWL-DL complexity. We performed the complexity analysis against existing reasoners, and then we discussed some of the results. So, so pretty much, I should also link I link in the paper the OWL complexity calculator, but pretty much what we did for the axiom mapping was that for each complexity letter, we determined which OWL axiom falls under that complexity. So we've programmed all of these OWL-DL axioms. For the most part, we're still working on qualified cardinality, and we've then mapped them to the specific complexity letter. So since we have pretty much example RDF from the validation ontology for each of these axioms, we were able to run each axiom one at a time in the form of unit tests for our reasoner and also through Protege for existing reasoners. So pretty much what we did was a DL complexity analysis, and pretty much the question marks you're seeing here are still tests that I have to finish running. So for example, this for all R.C, which is universal quantification, permanent fact++ and pellet should support universal quantification, but for some reason when we ran our test, we weren't seeing the expected output. So for that test, I have to kind of examine it further, or maybe try another example. And then these reasoners also should support qualified cardinality, which is Q, which we don't quite support yet, but we're working towards it. but for some reason we couldn't see the expected triple in the existing reasoners either. So that might be why we're not seeing it in our reasoner as well, because maybe the formulation is incorrect. So actually, by doing this evaluation, it allowed us to find potential mistakes within our examples or our representation. And it allowed us to really hone down on having a accurate reasoner. And so pretty much from this evaluation, you see that SQuARE is able to support everything so far except qualified cardinality, um, which which Pellet seems to do, except Pellet doesn't support universal quantification of data types. Um, Pellet, which was the closest to supporting everything we support, doesn't support everything we support. But then you have the other reasoners as well, like Hermit and Fact++, which is supposed to be efficient, but Fact++ doesn't support a lot of things, whereas there are a few things Hermit doesn't support as well. So there is also more than just customizability. There are some benefits um, to creating our own reasoner for supporting some of these axioms. Right, so we are close to the end of the hour, and I do want to leave some more time for some questions. So pretty much I'll just conclude by again saying that we've built our own reasoning engine by encoding OWL axioms as SPARQL construct queries, and in the process of testing our engine, we've created a validation ontology that other people can now use as a learning resource to see example formulations of existing axioms or as a way to test their own reasoning engines. And we make all of this publicly available. And I link the resources in the slide, which I'll share with everyone. And so pretty much, as I mentioned, part of this work is towards building a hybrid reasoning framework. And we've already built mostly, except for qualified cardinality, the deductive reasoning component, and we've already implemented the backward chaining component. So using that backward chaining component, what we're working towards next is abductive reasoning. However, a challenge is that with abductive reasoning, you may have an intractable amount of explanations. So we're working towards finding a representative set. And the idea is to apply this in a clinical reasoning setting where this may be used to recommend treatment options or potential diagnoses for chronic illnesses such as diabetes.
All right. So thank you, Sabbir. Let's thank Sabbir, and then what I'd like to do is I'd like there to be questions that we will record, and then I'd like to reserve a little bit of time where I'll stop the recording and we can have other questions or issues that should be off the recording with respect to helping Sabbir improve the slides, the presentation, that sort of thing. So do we have questions related to the content of Sabbir's talk?
Yeah, Matt, you can go ahead.
Yeah, this is a really cool idea. But I was wondering, so you're manifesting all these triples kind of early, and you're storing them separately. But I was kind of curious because you are growing the number of triples you need to search over. How does your search time and query time compare to if you're doing a search with inferencing using one of these other tools?
Right. So some of these other tools will execute reasoning in milliseconds, right? Hundreds of milliseconds or less. So we are slower than these tools in that sense, um, where so pretty much we are doing um, we're querying a triple store endpoint, and then we're writing back to the graph. So those operations take time in themselves, and then the writing back to the graph might result in the another axiom or a previous axiom executing again, right? So our execution time is more so on the order of seconds, um, or maybe 1 or 2 minutes even, whereas other approaches are much faster, right? So we're not necessarily um, quite there in terms of speed, but if you can wait for it, I guess, it may some of the benefits of being able to write your own rules may outweigh speed concerns.
Yeah,
So,
definitely. Oh, go ahead, John. Sorry.
well, you may have been about to ask this, man. What you just described is sort of what some people have called sort of a reactor pattern. If I understood what you just said, is the reasoning. You have to wait till the evaluation is you're sort of complete. It's like a lazy evaluation kind of a model where you maybe your partial reasoning will be modifying the graph, which in turn affects your downstream reasoning, and ultimately you've got to wait till everything settles, if I'm not mistaken, for
Well, right.
the actual result.
In a sense, you have to wait till everything settles to have everything that's been inferred. But as things are being inferred, they are being added to the graph. So you don't necessarily have to wait for everything. You can still you see the updated graph as it goes along.
So you can
Right.
still hit your graph while your reasoning is completing.
Yeah, so you can still hit your graph and you can see updated knowledge in the graph, even though it might not be the complete set of updated knowledge quite yet.
Do you ever have reversals?
Reversals?
Do you, well, how about reasoning modifying an assertion that you may have previously written?
So we don't, which is partly because of this idea that you may want inconsistent knowledge to exist in the graph, right? So you don't necessarily want to get rid of earlier knowledge through this approach. However, you could use something like Shackle to search for these inconsistencies. Or so you could imagine writing a reversal agent, which may use some kind of shackle constraint to find these inconsistent assertions, which you may then want to resolve in some way. But this approach is just creating the assertions themselves. So you can imagine it could be like quite simply, you could just search for all the owl nothings on the graph, right? Those correspond to the inconsistencies, but there might be other patterns which inherently are inconsistent without it resulting in owl nothing, and you might write a shackle constraint rule to find those patterns.
I guess what in this kind of additive scenario, particularly where you've got this partial information, I'm just kind of wondering in my mind how, why why wouldn't it naturally in some cases lead to some of your previous statements being perhaps overridden, not due to inconsistency, but due to this. I'm now, based on my reasoning, I need to change this. I guess that would be again, that would be a rule that you would write, right? You would, if such a thing could potentially happen and you were able to detect it, you would write a rule that would do that. So I guess you would take that into
Yeah,
consideration.
so you'd have to do like graph modifiers to do that, right? So it's a little bit more complicated than what we're doing. We're just doing graph constructs. So we're just adding stuff to the graph, only if it doesn't already exist in the graph. So at least, so if it already exists, it's not like we're adding duplicate information.
I guess being somewhat risk averse, Sabbir, I'm just wondering how do you undo stuff other than totally removing it? You know,
Right. Yeah. And
how
so,
do things you got a
uh,
lot of stuff changing and modifying, and how do you? I mean, part of the answer is having a foundation of nanopublications and stuff like that, which help
yeah.
you
So,
out.
and actually, through the use of nanopublications, you can kind of find what um, information was added through the reasoning engine. Because as I mentioned before, there is a provenance piece that gets added, explaining why the assertion was added. So you could search for that provenance piece, or you could even run the backward chaining agent, and then you'll see all the rules that could have resulted. But to actually do this reversal would probably require some additional implementation. All right, so I saw in the chat Deborah had a question. I'm just trying to figure out how to pull up the chat here. Okay, so Deborah's
It's almost an existential question on her part.
yeah. So to follow up, is there enough to support a truth maintenance system behind this? So this is probably
So it follows up on what you were just discussing. So the truth maintenance says, if something got updated and some other inference was based on this, then I need to really take out that inference. And so I think what you're saying is it's possible with the nanopublication information, but you currently don't have infrastructure to support that. And at least within your thesis, you're probably not going to do that infrastructure. Is that right?
right. Yeah, that's a good point. Right. So
Yeah,
if you have like a rule and the antecedent resulted in a consequent being added to the graph, but then you get rid of some part of the antecedent, how do we modify the consequent? So that is an interesting question. So I imagine we could build a truth maintenance system within YIS, but I don't think we're quite there yet.
Right. So Classic had the same, in early description logic, had the same kind of need. So it had procedural attachment. So you could run an arbitrary function and add something, but you couldn't just, there was a contract if you were going to make those additions, that you basically provided enough breadcrumbs so that Classic's truth maintenance system could pull something back out when it became not supported any longer.
Right.
And I think we would do the same thing here.
It does seem like an interesting extension that maybe a graduate student can work on in the future.
so kind of following on this point, because I think it kind of is it reveals a bit more about how things work. You mentioned that in addition to the assertions being written in nanopublications, that the provenance is being recorded and is sort of explaining why, right? Why a particular assertion is being written, why this construct happened, right?
Mm-hmm.
So I would think that if you're going to have smart support for backing things out or changing things, that provenance, reasoning over that provenance is going to be critical. You're going to want to, or at least utilizing that provenance to realize I did this before, and this is what I did.
Right, but right. So I did think about this a little bit when making the backtracing capability. So the provenance could be useful, and it is probably the easiest way to go backwards and find out where things came from. But you also want to be able to do it in a way where if you didn't have that provenance, you still are able to go back to figure out where this came from and how to remove it or something, right?
Yeah, so you need basically to keep the dependencies. You need a dependency graph so that you know that something depended on this And if this went away, the thing that depended, if the only reason that something is in the graph is because of the thing that went away, then you need to pull it back out. But if it was there for an independent reason, then you shouldn't pull it out. So, you know, it's not as simple as it might seem.
Well,
And
also
John,
depending upon it.
yep, yep.
Right.